Hi, everyone, and welcome to the third webinar in our Future of Cooling for COP26 series, organized by Future of Cooling program at the Oxford Martin School, University of Oxford. My name is Rinaldi. I'm a research associate and Oxford Martin Fellow in the Future of Cooling program. In today's webinar, we will look at the role of technology and innovation in the future of sustainable cooling. As we know, the technology plays a very vital role to satisfy the global cooling demand. Technology itself can be roughly divided into active cooling technology, which requires energy input, and passive cooling technology, which requires minimal or no energy input. Today, we are lucky that we have brilliant speakers in the session. We have Iain Campbell from the Rocky Mountain Institute, and hopefully we'll have Diana Urge-Forsats from Central European University. So before we start with Iain's presentation, I will explain a bit how this webinar will work. So first, the speakers will present their presentation, and in the end of the presentation, we'll have some discussion, and then we'll take questions from the audience. If you have questions, please press the button on the bottom right corner of your screen. There is a Ask a Question button, and then you can press that, and hopefully we can be able to answer your questions at the end of the session. Now I will introduce our first speaker, Iain Campbell from Rocky Mountain Institute. So Iain is a senior fellow at RMI, where he leads the Institute's building practice. Before joining RMI, he pursued a successful business career in energy efficiency in buildings, and he held various positions with Johnson Controls and also served as the president of York International. At RMI, Iain helped to launch the Global Cooling Prize to drive climate-friendly technological innovation on room cooling units. Iain, over to you.
Okay, thank you, Rinaldi, and good morning, good afternoon to everyone. I see we have a very international group of attendees here. So I just wanted to kind of start off with just sharing a few slides, a little bit of context and a little bit of background, and then start to dive into some of the technology spaces and perspectives there, and then look forward to a robust discussion after helping tee this up. So if you'll just bear with me, just need to share the screen here and take you through a short presentation, as I said, which is really to help set the scene for the discussion. A few words first about RMI. RMI is a non-profit organization. At RMI, our focus is really just on helping support the acceleration of a transition to a clean, zero carbon future. And if we look at cooling, I think we know that cooling in all its forms today is responsible for close to 10% of all annual greenhouse gas emissions. And so cooling is an area that's been in our sights and has been in our sights really for the last 5 years. I think we started our focus in cooling in about 2017, just after the Kigali Amendment to the Montreal Protocol back at the end of 2016. Some of the work that we've done in this space, we led the initiative of the Global Cooling Prize and learned so much from the participation of many innovators around the world, and look forward to discussing and sharing some of that. We also developed a sustainable space cooling primer and compendium for the World Bank, and next month we launch a sustainable urban cooling handbook. That's along with UNEP, Global Covenant of Mayors, the Clean Cooling Collaborative, and Mission Innovation. So enough about RMI. Let's maybe jump to some of the context here. So I like to start with this slide because, you know, we kind of think about cooling today being 10% of greenhouse gas emissions, but when you look at the what's coming in the future and the trajectory that you're on, there's even more reason to be concerned. And this chart, let me just take a moment to explain this. The blue bars should be read in conjunction with the axis on the left. and that is basically, I would call that normalized latent demand for cooling. So it's basically cooling degree days factored by the population. And there's a representative group of countries here, and you can see, the scale of normalized demand. Obviously, India would be the largest there, and then the orange, short orange bars are the level of penetration of air conditioning in households. So it's focused on residential, which is where we expect to see most of the growth. And you can see that places like Japan, United States, South Korea, they're very high levels of penetration, but relatively low normalized demand. Where we see very high future demand coming, places like Mexico, Brazil, Indonesia, India, Nigeria, Egypt. And so it's just a representation of countries, and you get an idea as to what the future of cooling is going to look like as adoption of cooling spreads into countries where there is the greatest level of normalized demand. And the trajectory that we're on, and then we'll jump to the topic at hand, but I think this context is important. The trajectory that we're on would see a huge impact on power systems around the world, corresponding impact on emissions and climate, and also an impact on consumers, because and end users, because the cost of the life cycle costs really do outstrip the first cost of cooling by a very significant factor, and we'll get to that as we get into the discussion. But from a power systems perspective, I think cooling's unique in the way it drives peak load. Any country which has high penetration of cooling, on the hottest days of the year, cooling can be up to 60% of the power consumption where there's a high degree of penetration. So what that means is there's a correlation between the adoption of cooling and capacity that's needed to power cooling, at least the technologies that we have today on the grid. And you can see the estimate that when we get to 2050, there could be a 400% jump in capacity needs associated with cooling or driven by cooling. And then the impact on emissions and climate. And I think everyone on here, I'm sure, knows the direct emissions of refrigerant release and the indirect emissions associated with energy consumption. So it gives it a flavor of what the path is if we stay on the trajectory that we're on, which is one where the performance of technologies within this space continues to improve incrementally, and we're not adopting the best available technologies, and that's another issue which I want to touch on as we get a little further into the discussion. So how to address cooling sustainably, and our view is that there's a natural order of things, and the first is you reduce cooling loads and work to reduce cooling loads. And that actually starts off not at the building level, but at the urban level, with urban form and design and incorporation of nature-based solutions into the urban environment to ensure that that our cities and our urban areas are not effectively mini ovens that are heating up beyond the temperature in the area surrounding cities. So working on urban design and form is really important. And then at the building level, the things that you can do to reduce cooling loads, and depends on the climate zone you're in, you may not need active cooling, or you may not need vapor compression cooling. But in hot and humid climate zones, you significantly reduce the load that's being served. So reducing cooling loads is really important, and certainly there's a reason why they're in this sequence, because if you don't start with reducing cooling loads, you end up oversizing cooling equipment. Once you've done what you can to reduce cooling loads, you look at how you can serve those cooling loads most efficiently and sustainably, and then optimizing. And we like to think of, how do you make systems part time and part space, so they only operate when they're needed to, so they're responding actively to demand, and you have equipment and systems that can modulate supply to meet demand so that you don't generate wasteful cooling. And then there's a whole operations and maintenance piece, but a big part of the optimize is what I would call smart cooling. Not going to touch on the passive cooling in depth at this point, because I think that's what Diana's planning to discuss. But wanted to talk about, just at a very high level at this point, about serving cooling loads efficiently. And there's multiple technologies, but the majority of them are based upon vapor compression technology, and vapor compression technology has been around for over 100 years. It's, from a first cost perspective, has become very cost efficient, and that's something that the market is very orientated on, is the first cost of equipment. But it is an effective and very convenient way to provide cooling to spaces that can provide thermal comfort to people. So of the multiple technologies, you kind of have the fans and evaporative coolings, and in dry climates they can be very effective. As we get to hotter, more humid climates, you then tend to be looking at vapor compression, as well as some other technologies like absorption and adsorption that, depending upon the availability of heat sources, can be very effective. And one of the big determiners of what technology goes in is what is the scale of cooling that you're looking to provide. And this graphic kind of effectively talks through that. But kind of a few of the key takeaways here is that pretty much in any of these equipment categories, the best available technology is typically around 2 times more efficient than the lowest first cost products in that market or in that category. And yet it's the lowest first cost products, especially with the smaller products where you don't have professional or informed buyers, that there's a concentration of purchases on the lower first cost technology. So the best available technology is not being widely used. The vapor compression systems that are able to use low temperature heat sinks deliver significantly more efficiency. And so that's either water or ground or geo exchange. And that's why district cooling and water cooled chillers in the right application will deliver significantly greater efficiencies. And then, similar to the dialogue about best available technology, most refrigerants in use today still have a global warming potential of over 1,800 times that of CO2. But there's best available technologies, whether that's natural refrigerants or synthetics, that sit below 10, and they don't have high penetration, and they don't have high penetration because they're more expensive. And we'll get to that when we talk a little bit about importance of regulation in the space. I spoke a little bit about optimizing to enable part-time and part space of cooling. So this is just smart cooling. I have a personal belief that, unless you have you're in a process cooling application, to not have inverters or variable speed drives is just criminal. When you think of what that means in relation to energy consumption, and you think of what the very small incremental cost of those technologies are, but smart cooling really important. This is what I was meaning about the impact from a life cycle cost. This is what we did in India. So we said, okay, let's look at the entry level air conditioner. The blue bar represents first cost. The orange bar, stacked bar, represents the operational cost, so the cost of electricity. And by the way, the residential tariff in India is actually subsidized by the government. So this is kind of, in a way, understating what would be there in a regular market. And then we looked at the best available technology and looked at its operating cost over a 10-year lifetime. And it's kind of, when you look at this chart and you realize that over 80% of the market is at the entry level air conditioner, which costs almost twice as much over its life, that you realize that we have some challenge. And through the Global Cooling Prize, it's not just the best available technology. We know that that there's technologies that can go much further. And through the prize, we threw down a challenge of, we're looking for a 5 times lower climate impact cooling solution. And we had applications from over 150 participants. We selected 8 finalists. We did lab testing, plus we did field testing. We took over a 14-story apartment building, put 1 unit in each on each floor, and the requirement was to hold temperature and humidity at no more than 27 degrees centigrade, no more than 60% relative humidity. And basically the white bars are the units that met those conditions. So they met the temperature and they met the humidity constraints. The long white bar is the baseline unit. So that's the entry level air conditioner. You see there's a blue line, which is a 5 times lower climate impact. And you can see that we had 2 teams, and this was consistent through the field test, that were considerably below 5 times lower climate impact. Those code names were Team Polar and Team Ice. And we now know that that was Team Gree and Team Daikin, who were the eventual winners of the prize. So we know that we have far more efficient and sustainable know-how, even though these aren't products that are available on the market today. But we know that there's technologies that can change the trajectory of that future that I touched on in the first slide. But the issue is not, I would suggest that the issue is not a technology issue. Is there more technology can do? Yes, of course there is. Would better technologies help accelerate a transition to a more sustainable future of cooling? Yes, they would. But we have a market issue, and there's a range of market barriers. And probably the biggest one is often the people that are buying or purchasing cooling aren't the ones that will be paying the energy bills associated with the consumption of that cooling, or don't feel that there's sufficient certainty to warrant a higher first cost. So there's a range of market barriers, and I think that those market barriers result in market failures, and market failures where the lowest life cycle costs do not win out, and we leave best available technologies largely sitting on the shelf. And what that says is we have a market failure. There's a need to shape the market, and there's a need to shape the market from a policy and regulatory basis, but also in relation to funding and supporting instruments. So that was really just what I wanted to touch on to kind of get us started within this space. Oh, I've got one more slide to show you. This is work we did for the World Bank, and we actually did, okay, so what's the opportunity cost of not shaping the market for sustainable cooling? And we looked back over the last 20 years and said, okay, what if instead of the trajectory that we took over the last 20 years, we took a trajectory that would deploy best available technology within the market, but only where that technology has a lower life cycle cost, delivering net present value benefits after being discounted. And we saw that the impact of cooling from an emissions perspective, from an impact on power systems perspective, would be about half of where it is today if we'd acted 20 years ago. So there's a substantial opportunity cost, and it kind of gives you a feel as to what that future could look like if we are able to make the jump to best available technology with a lower life cycle cost, and more sustainable solutions. So thank you for listening to the presentation, and I look forward to trying to answer people's questions. And if folks want to know more about the Global Cooling Prize, we've got a lot of information on our site that's still up about the winning technologies. But also happy to answer questions here. Site for the Global Cooling Prize is globalcoolingprize.org. Thank you, Rinaldi.
Thank you very much, Iain, for the presentation. I'm sure there are a lot of questions, and we can discuss. I also have several questions, but I would like to go to the questions from the audience first. First, non-technical question: can we get access to the slides from Caesar? I'm sure we can provide the link to the talk, because the talk is recorded. Another question is from Radhika Koshla. What do you see as the next frontier of technology, given that the vapor compression has been around for 100 years? And even the winner of Global Cooling Prize are from the same technology. And where to and how do you see the shift of the next generation of cooling technology?
Yeah, so there's a number of things which we kind of seen on this journey that are exciting, but I think there's still some ways out, and still questions of whether they're niche market solutions or mass market solutions. So we had quite a few solid state cooling solutions that entered the prize, and actually one of the finalists was a barocaloric solution, but they unfortunately were not able to get to a working prototype in the timeline of the prize. The solid state solutions obviously avoid the challenge of not having challenge of having a refrigerant. And we know the issues that we've had in the past, and there's still concerns as well about using synthetic refrigerants. And the natural refrigerants that we have, depending upon the application, there's still some concerns about those, whether that's toxicity or flammability. And there's a lot of applications that they work for, but I guess on the refrigerant side, I think I would say I'm not sure that we've found the perfect refrigerant, and that may still be some way off. So solutions that don't have a refrigerant can be assured to be more sustainable in relation to not having unintended consequences of refrigerants leaking to the atmosphere. So that's a positive. The challenge is getting to the efficiency levels of vapor compression. And vapor compression, because it's been around so long, but also just because of the dynamics of the technology, it actually has efficiency levels that, although some of the solid state solutions have promise, they're not today as efficient as the vapor compression technology that's in the market. Where I do think that there's opportunity, though, is to be able to, some of these technologies to be able to enter niches within the market, where their attributes are actually likely to provide a better solution. And one of the examples I like to use on this is thermoelectric. And, if you think of, refrigerated vending machines that deliver you a cold soda, a cold can or bottle of soda, and they're running 24/7, wouldn't it be smarter if when you make your selection, that can of soda gets dropped into a thermoelectric sleeve, and in 7 seconds it's at the same temperature as it would be as if it came out of a refrigerator? That not only is a much more sustainable way of cooling those cans of soda, but also a much more economic solution. And so, it's just a small example, but you can see how certain attributes of these technologies can fit into niches and spaces within the market that may even cause us to change our thinking about cooling. And, do we cool spaces, or is it people that we're trying to cool? And if we're trying to cool people, why do we cool the space around them? And is there a better way to do that? So what I don't see as a clear pathway is there a next generation technology that just comes in and displaces the vapor compression technology that's predominant in the market today? I'm not sure. But is there technologies that can bring different forms of cooling that can be much more sustainable and efficient? I think some of these emerging technologies do show promise there.
All right. Thanks.
Sorry, that was a long answer, but that was a complicated question.
It's an open-ended question. Still in the front of specific cooling technology, there is a question from Garrett Fultner. Would you agree that especially thermal-driven sorption cooling could offer a significant and currently untapped potential as a sustainable cooling solution? For example, driven by waste heat and also geothermal and solar thermal energy.
Yeah, totally. And it's one of the solutions where when you have access to waste heat, it has to be fairly high grade, but when you have access to waste heat, it's the lowest cost solution that's out there. It's not very efficient in relation to just conversion of energy to cooling energy, heat energy to cooling energy, but if it's free and you don't have to generate it, it's a great solution. And I think that, probably the bigger challenge as it is with the best available technologies is the adoption of the technologies the right fit technologies that we have today. And, we see this in the place that I look at to see some of the best practices is in district cooling. And the reason I look at district cooling is because, you've basically got investors that are investing in a thermal system, whether it's district cooling or district cooling and heating, and they're going to own and operate that system for the next 20, 30 years, whatever the concession term is. And so they're motivated to put in the most efficient, lowest life cycle cost technology that they can get access to. And so that's why you tend to see some of the best solutions there. And we typically, or often will see that, yes, they're using electric centrifugal water-cooled chillers, but they also have absorption equipment if they're able to make use of any available thermal energy within that district cooling facility. So absorption, I think in particular, is well suited to these big central systems because you do have that greater opportunity to access heat sinks to reject heat too, but also heat sources to capture heat. We actually saw some interesting things with the prize with, and this is maybe a little bit off the topic, but interesting things with the prize where we had a number of competitors that were actually using the waste heat coming out the back of the condensing unit of the vapor compression air conditioner. They were actually using it to recharge their desiccants for managing the humidity and the putting moisture out of the air. So it was just interesting cycle there of, you know, it's one of the other things with cooling is, you know, you create heat and it's anthropogenic heat and it further heats the urban environment because of the rejected heat coming out of the back of air conditioners, and being able to utilize that in some way. And obviously when you have large scale plants, you have greater ability to do that, to capture those kind of energy sources. It's a good question.
Yes. So a relevant question here from Malcolm McCulloch. In many countries, both heating and cooling is required. What are ways that these two needs can lead to synergies, and with what ways they can lead to dissonance? So both heating and cooling here.
Yeah, and so it's interesting. My my father lives in England still, and I was having a discussion with him yesterday. Just yesterday, he said there was article about, you know, how we have to all transition to using heat pumps now because we have to decarbonize heating. And but this article says about how much more expensive a heat pump is than a gas furnace. And so I was sharing with my father in this discussion. I said, yeah, but what the article's not telling you is that not only do you get this heating device that is probably going to be about 3 to 4 times more efficient in converting energy to heat as your gas furnace is today, but you also get a free cooling device because it will be able to operate in reverse cycle. And my mother, who's always complaining that it's too hot in her home, will actually have air conditioning now. So you can't just look at this and say, hey, the heat pump is more expensive than a gas furnace. You get far more utility and you get far more efficiency with a heat pump, and you know they continue to be refined for colder climates. But it's something that we're seeing. I mean, another example was up in the Pacific Northwest here in the US, where we had very high temperatures during the month of July, and you know most of the homes in that part of the country don't have air conditioning, and there's a lot of people thinking about going out and buying their first air conditioner and getting it installed in their home. And that's going to be an expensive proposition, especially if it's a central air conditioner. And if you're going through that, does it make sense to accelerate the transition from gas combustion in a furnace for heating to a much more efficient and environmentally sustainable solution, a heat pump that in reverse cycle can also provide you cooling in the summer for the days that you may need that? But if we were to run another cooling prize, you know, the one that we did was for a dense urban environment for existing buildings in a hot and humid climate zone. If we were to do another one, I think that we would target more temperate climate zones, and we'd be looking at heating and cooling as a combined solution.
Yeah, that will be very interesting.
There's great products already on the market, but we saw with the prize that if you ask the right questions, industry can show you what the future looks like. And that's what we got with the global cooling prize. You know, we were seeing products or technologies that were 2 to 3 times lower climate impact. We said, can you show us something that was 5? And we had people within the industry and we had innovators say, yeah, we can show you that. And they did.
Yeah, I will link up that to the next question, again from Malcolm McCulloch. How can some of the winners be accelerated into wide-scale adoption?
Yeah, so great question, and it comes back to shaping the market. And let me kind of share with you the challenge here. So one of the winners, GRI, has made a commitment under UNFCCC leading into COP26 that they will bring a 5 times lower climate impact solution to market by 2025. So they've made that commitment. The issue is, will anyone recognize that level of performance and be prepared to pay a premium? Because there is going to be a cost premium, even though the technology will, again, it will be less than half the cost from a life cycle perspective. And if you, I'll talk about the market in India. In India, you know, like many countries, they use SEER ratings to assess the performance of air conditioners. And they have a performance ladder that sits above the minimum energy performance standard. So the minimum energy performance standard, I think in India, is probably a 3.1 SEER today. And then, you know, you can go from a 1-star to a 5-star. Well, a 5-star is anything that's over 5 SEER. Unfortunately, the equivalent SEER for the unit from GRI, if SEER was able to measure all the performance attributes of the winning unit, and that's another question, was over 10. And so it's so far beyond the performance ladder that it can't be recognized. It's going to be compared with 5 SEER units that operate using twice as much energy for the same cooling output. So what we have to move to, I believe, from a policy and regulatory perspective, is we need to anchor to the best available product for the top level rating of our performance ladders. And then we need to let the top pull up the floor. The way that it works today is we set a floor and we build, which is the worst performing product that you can buy in the market, and then we build a performance ladder up from there. And you know, if we want to be led by technology, you don't anchor yourself to the floor, you pull yourself up through the ceiling, and our system doesn't do that today. And that simple change, I mean, they've done it in Japan with the Top Runner program, and not exactly as I've described, but it's got some similar attributes, and it accelerates the penetration of more efficient and sustainable equipment within the market. And we can't assume that manufacturers are just going to be able to do this on their own without some market shaping, because without market shaping, we're just going to be rooted to the floor. And you know, when you think of the power of ingenuity, human ingenuity, and the power of technology, we can't be anchored to the floor, or we're never going to get to where we need to go.
Yeah, so there are some questions related to your final remark about market there. For example, what is the scope for financial incentive from companies or government to take some of the cost premium of the cooling prize winners? Similar question also being posed here. How can development banks support technological innovation and scalability? I think it's a similar question there.
Yeah. So, you know, on the first one, there's this link between what happens when more cooling goes on the grid and what that does to our power systems, because we know cooling drives peak load. But this gets even more challenging because we're working and investing to decarbonize power systems around the world and to go to renewable energy sources. Well, the profile of generation of renewable energy sources isn't a perfect match of the profile of cooling. And the cooling, at least residential cooling, is going to be used more late afternoon through the evening and often through the night to maintain conditions so that people can be comfortable in their home and can sleep. What that does is it just makes the duck curve of load profile even worse if you understand the problem that California has with the amount of solar penetration they have on their grid, of how that kind of shapes the profile of the kind of load that has to be met somehow outside of the what's met by renewable energy. So there's a direct correlation there, and it would be cheaper to subsidize the first cost of air conditioners that are very efficient, let's say 5 times lower climate impact, than it would to add the capacity to the grid to supply power to that unit on the hottest days of the year. But I get the challenge. The challenge is the governments want to be seen to be subsidizing air conditioning, which is in many parts of the world is viewed still as a luxury product. But there's got to be an answer between the challenge. I mean, we did rough calculations that told us that for every dollar that is spent on a room to buy a room air conditioner, there's probably 80 cents that needs to be spent to add additional capacity to grid infrastructure to deliver power to that unit. And it's just, when you look at that, you just have to say there's got to be a better way of doing this through utilities. But then that gets complicated because you've got to say, okay, can a utility rate base a subsidy for an air conditioner and recover that cost? And so there's things that you have to look at within the system. I do think that there's an opportunity though and there's folks looking at this to actually run some pilots, and I think that's a good example of where some of the development banks could get involved, is to be able to be involved in demonstrations of market-based solutions that can enable adoption of these kind of technologies. And I think that's what we need there next. I don't think we need to give them subsidy to manufacturers so they sell lower cost equipment. I think we want something that can sustain and scale, and the best hope for that, I believe, is enabling utilities to rate base a subsidy for super efficient air conditioners, and save a lot of money in the system as well because of not having to put in capacity that's only used on the hottest days of the year.
Right. There are also questions about alternative technology from the audience, but before we get to that, I would like to ask: do you think there is a global lock-in with vapor compression technologies in the world? And second question is, does this solution will also be global, or is it more local as country per country or even per cities basis?
Yeah, so is there a lock-in? I think the answer is yes. And why do I say that? If you live in one of the heat stress cities in India, I'm going to use India again as an example, and you're in a small apartment building, maybe 60 square meters, and you're there with your family, and there's there's your family size is 6 people, and the families finding it difficult to sleep at night because of the high summer temperatures. And high summer temperatures, we're talking of getting up over 45 centigrade. You can get a solution installed in your apartment for $534 as a vapor compression system. It's not going to be efficient. It's going to use R22 refrigerant, although that is transitioning now, but that's still one of the predominant refrigerants there. But your family's going to be able to sleep at night, and you're going to have comfort. And so, it's one of the challenges in passive solutions is they have to be, not always, but they largely have to be designed into a building when it's being constructed or going through major refurbishment. When you look at this family in India, they're not thinking, we're getting to 45 degrees centigrade and I can't sleep. They're not thinking, I need to insulate, I need to put film on my windows, I need to do something about putting in increased natural ventilation and airflow. They're thinking, I need a damn air conditioner. And they can get one installed for $534. So that's why we did the cooling prize, because we were trying to say, we know this is going to happen anyway. There's 10 units being sold every second. Let's make those units as good as we can. We need to do all the other things and work on them, but let's make those as good as we can. So is there one solution for every market, for the world, or does that change? I think climate zone impacts it. And I think that in different climate zones, the solutions are potentially different, although I do largely still see vapor compression. But the one I touched on earlier was district cooling. If there's an opportunity to step into district cooling in an urban environment where you've got enough density and diversity, that it's going to be your lowest cost solution, and it's a solution that you can make more sustainable. I mean, there's a great example of, and not every city has a lake by it, but Toronto actually uses Lake Superior as a heat sink, but also for free cooling for most of the year. So there's a district cooling system, and all they do is take cold water from the bottom of Lake Superior, chill it just a little bit more, and distribute it to all of the connected buildings within the city. And you can't displace the efficiency of that kind of approach with another refrigerant technology, because such a large part of the cooling you're getting is free, and it's nature based. And because the lake freezes through the winter, the temperature down at the bottom of the lake is cold throughout the year. So the ability to be able to even City of Paris, for their cooling system, they actually utilize the River Seine to increase the efficiency of their cooling system, using that as a heat sink. And there's things you have to be careful about, you don't overheat the water and what have you, but these are approaches that you can't do one home, one apartment at a time. You have to do it at a city level. When you go to that level of scale, there's opportunities to get so much more efficiency, and to do that by using diversity of heat sources and heat sinks.
Okay, you briefly touched on the spatial differences in cooling. There is a question related to that here, that on personal cooling, given that there are already technologies for personal cooling, why haven't this been championed and mainstream? A question from Richard.
Yeah, That's a great question. And I think, here we're talking about wearables. So how do you provide comfort to a person? And, we have one of our offices in that we developed as it's a net positive building. And the way that we looked at that building was to design it so that we would not provide any heating in the winter. So basically, what we did was we set a range of temperature and said we believe that we can ensure thermal comfort for people by giving people the ability to get localized heating or cooling, as long as we maintain temperature within this range. So, it's not saying, hey, we're going to leave the temperature to flow anywhere between -30 centigrade and +45 centigrade, and here's some heating and cooling stuff and figure it out. This is saying, hey, we're going to maintain a temperature that's, say between 14 and 28 degrees centigrade. And and some of the things that we have used was electric coils for heating in chairs, little rest for keypads on the computer that would heat and actually send heat through the wrist, which is warms people up further. And again, for the feet, because it's basically hands, feet, and heads that will get cold. And then also localized cooling devices, which was really, really fans and being able to manage ventilation within your space, and then flexibility in relation to expectations of clothing and what have you that people would wear. And those things significantly reduce loads because you're now working within a much better range. I mean, one of the worst things I think here in the US is, everyone talks about 72-degree conditioned air. Like that's where you have to be at, and we have to be at there precisely. And that precision requires huge amounts of energy. If we just set ranges, there's significantly less energy we use, and the wider we go, the more we give people an ability to get localized thermal comfort, the greater that range is that you can go to. Why hasn't that taken off? It's complicated to do, and you're working with human behavior. You have to transition human behavior and expectations of what thermal comfort is. And for an organization like RMI, and you look at what our mission is, our staff, they work to our mission and they believe in our mission, and they're prepared to go through a little bit of discomfort because we're demonstrating something here which we think has potential to scale. I do think there's something there in wearables, but the issue, we kind of touched on this with, does vapor compression have a lock-in? I think it does, because it's actually defined what we think of as thermal comfort. And I think it's going to take, I don't know that wearables will displace. I think they can help, and they can reduce the amount of reliance we put on vapor compression. I don't think they're going to displace this technology that has a lock-in, because we've become conditioned to think of that's how we get cooling.
Okay, we're approaching an hour mark, but I think there's still time for this one last question, still on alternative technology. Is that, what's your view on radiative cooling technologies? Do you think it's going to be an alternative to the vapor compression technologies?
So I think, radiative cooling is one of the most exciting things with some of the new materials, nanomaterials that kind of people are working on in this space. I think of radiative cooling more as a supercharged passive cooling, reducing load opportunity, as opposed to perhaps an active cooling solution. But yeah, I think it has great promise and is probably one of the next waves of technology innovation. It's still very early stages in our understanding of which materials, have the opportunity to both reflect heat, but also emit infrared heat in the right wavelength. And there's exciting work that's underway in universities today. I think, like many passive solutions, one of the challenges is how do you get it deployed? At some point, like we do with white reflective surfaces, it has to go into building codes if it's going to be deployed widely. But yeah, some of these technologies hold significant promise. Again, I don't know that it's if you're in a hot, humid country, that this is going to displace the need for active cooling. But I think it can take a significant dent in the cooling load that you're needing to serve, such that in more temperate or moderate climate zones, it may well prove sufficient.
Thank you very much, Iain, for a very interesting discussion, and also it's been a pleasure to have you in our series. And thank you for stepping up also to fill the whole session, because we're coming to the end of our section now. So thank you for the audience for attending, and don't forget, next week the series will continue with talks on models for sustainable cold chains. So thank you all for joining us, and hope you have a great day ahead. Thank you.
Yeah. Thank you, Anaudi. Thank you, everyone. And that will be a great next session with my good friend Toby Peters. So tune into that one.
Thanks.
Thanks. Bye bye now.
Bye.